Consider a regression problem. That is, we are given a set of pairs, each pair consisting of x, which is an n-dimensional vector, and lambda, which is a real number. And we want to find some function f such that f of x is approximately equal to lambda. This problem can be solved by using the kernel method. That is, the function f can be chosen from a reproducing kernel Hilbert space. So we fix some kernel function and derive this space. And by minimizing this error function, we can find that the function f can be represented as a linear combination of the reproducing kernels, which is also expressed as this. As you can see in this form, once we transform these data points using the kernel function, finding these coefficients is just an ordinary linear regression problem. So by using some kernel function and linear regression technique, we can effectively solve nonlinear regression problem. In this video, we study the basic ideas behind this technique of kernel regression. Okay, let's start. To use the kernel method, we first need to specify a kernel function. In this case, the kernel function is defined on the d-dimensional space. So r to the power of d times r to the power of d to real number. And as usual, we write k of xy, and x and y are d-dimensional vectors. We also write this as ky of x. Okay, so this ky is a univariate function of d-dimensional vector. And as we have seen before, once we determine a kernel function, we can derive the corresponding reproducing kernel Hilbert space. And now, using the given points, let's consider the set of reproducing kernels parameterized by the data points x1, x2, and so on up to xn. And let's consider the subspace of the Hilbert space, M, spanned by these vectors. Okay, so linear combinations of these vectors, Cj, Kxj, where Cj are real numbers and j from 1 to n. And now we can define a projection Pm onto this subspace. Let's call this simply as P. So using this projection operator, any element f of this Hilbert space can be orthogonally decomposed into two parts. That is, f is Pf plus 1 minus Pf. So this is a projection onto the orthogonal complement of M. So this part belongs to M complement, and this part belongs to M. And we note that the inner product in this Hilbert space, 1 minus Pf times Kxj, where Kxj is one of these vectors, is equal to 0, because this one belongs to M, of course, but this one belongs to M complement. So they are orthogonal to each other. Therefore, the inner product, actually, this should be Hk here. This inner product should be 0. They are orthogonal. So f of xj, where xj is one of the data points, is equal to the inner product between f and kxj. This holds because we are now in reproducing kernel Hilbert space. And this is equal to, using the orthogonal decomposition, Pf plus 1 minus Pf times Kxj, and using the property of the inner product, we can split like this, and 1 minus pf kxj. But this is 0, as we have seen here. So this is simply pf times kxj. So as long as we are dealing with the given data points, we may assume that the function f is equal to its projection onto the subspace M. So f is equal to pf, which is equal to some linear combination of the reproducing kernels, kxj, which of course belongs to the subspace M. And from this expression, we can see that f of xi, I is again yet another data point, is equal to sum over j cj kxj of xi. And using the bivariate form of the kernel function, this is equal to cj k of xi and xj. We can represent this in a matrix form. So f of x1 up to f of xn is equal to the matrix k x1 x1 and k x1 xn and so on, k of xn x1 k of xn xn and c1 up to cn. Now, if we write this matrix as k and this vector as c, then the original error function, that is j from 1 to n, and f of xj minus lambda j squared, can be written as this. That is, so f of x, so this is written as k times c and minus lambda as a vector squared. So this is a norm in n-dimensional vector space. And now this lambda is a given vector, and this k is a matrix constructed from a given data set. And the only unknown is this c. So this is just an ordinary linear regression problem which can be solved by the least squares method. And we are done. What's nice about this kernel method is that by choosing various types of kernel functions, we can solve various kinds of nonlinear regression problems by using the technique of linear regression problem. Of course, the best choice of the kernel function may not be obvious, but still, it's a very powerful method. And we will see more concrete examples of this method in future videos. Okay, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.